Good afternoon, geometries. Hope you are doing well. All right, so here is your lesson. It's like a second half or a takeoff off of what we did yesterday. Because yesterday we established a real good solid base for dilations. We have the idea that we can perform them by multiplying each of our coordinates by the scale factor. And so today I just want to talk, real briefly about what would happen if we changed our center of dilation, and then a couple of different things that we can do with that. All right, so here we go. Okay, so first of all, make sure you turned in your homework, the Dilations Worksheet 1. If you had any questions off that, make sure you let me know, send me an email or something so that I can remember to go over those tomorrow with you. And then you do need your packet from yesterday. So we're going to be starting on page 244. So go ahead and pause the video right now and grab that if you don't have it out yet. If you need extra copies, please ask the substitute. I did leave a couple extra packets there for anyone who forgot theirs. All right. Okay, here we go. Performing and describing dilations on and off the coordinate plane. Okay. All right, so what we're talking about today is the center of dilation. Okay, you can kind of think of it as, if a dilation is something that changes the size of a figure, the center of the dilation is the center of that explosion outwards. Okay, so if you take a look at my picture here, you see this little red triangle and it's become this bigger triangle here. Well, if you trace back along each of the vertices, you see that they all meet at the same point, which is this point right here. So we would consider that the center of the dilation, that's the point from which those triangles expanded out. Okay, so think about what we were doing yesterday. What would you guess was our center of dilation? Because we never mentioned it. Ah, very good. So our center of dilation was always 0, 0 yesterday. Okay, we were just assuming that we were always expanding out from the center of the graph. Okay, and to be fair, that's what most dilations are. Most dilations we expand out from 0, 0. It's easy, we multiply our coordinates, there's nothing else going on there. Okay, but it's worth asking, what if we didn't want to expand out from 0, 0? What if we wanted our center of dilation to be on the figure? Or what if we wanted to expand out from another point in the graph? Okay, so that's going to require a little bit of movement. Okay, so they're at the top of page 140 or 244. We're talking about Kate again. Okay, so the very first sentence there, it says, in each of Kate's layouts above, the center of dilation was the origin. Now she considers some dilations where the center is not the origin. So remember, origin is 0, 0. Okay. It says Kate wants to dilate triangle ABC with a scale factor of 2 and a center of dilation at -2, 4. So she wants it to appear as if this figure is expanding outwards, okay, getting 2 times bigger from a center of -2, 4. Okay? All right, so we could draw some pictures, try and graph, -2, 4 and make it so that it looks like the figure expands out from there. But I want to run an idea by you. What if, because it's very easy to dilate whenever we're just at the origin, we just have to multiply by 2. What if we moved the center of dilation so that it was at the origin? What would that look like? Okay, well, it would basically be a translation, right? Okay, because my center of dilation right now is at -2, 4. If I were to pick up this entire figure, including the center of dilation, and move it 2 to the right and 4 down, the center of dilation would be at 0, 0, right? And if the center of dilation is at 0, 0, I can just multiply, which would be kind of nice. Okay, so let me see if we can make that happen, all right? So, I could move it on the graph, right? So at this point, over 2, down 4 would end up at 0, 0, okay? I'm going to move this point next, so over 2 and then down 1, 2, 3, 4. So I'm off the graph a little bit, but that's okay. Okay, and then this point right here, if I go over 2 and then down 1, 2, 3, 4 would end up about right there, right? Okay, so my figure looks pretty much the same. Okay, it's just been moved down. And here, I kind of like this because now I could just multiply all my coordinates by 2 and make this 2 times bigger, and that would be super easy. Okay, so let's do that. So I'm going to need some coordinates here because I don't know what these are necessarily. So that's going to be 0, 0, right? Okay. All right, this point right here was at 1, 2, and I moved it over 2, so it was at 3 now, and then down 4, so -2. So 3, -2 is where that ended up at. And so then this point ended up at 3 as well. I believe it was 2 less than that, so it's going to be at -4. Yeah. All right, I could multiply all these by 2, right? So 0, 0 times 2 is still 0, 0. 3 times 2 is 6. -2 times 2 is -4. 3 times 2 is 6. And -4 times 2 is -8. Okay. All right, this is going to go way off my graph, but I'm going to try and graph it just so you can kind of get an idea of how much bigger it became. So 0, 0 stayed the same, but 4, 6 is out here, -4 is down here, and then 6 is way out here. -8 would be much, much lower. It'd be like all the way down here. What do you think? Did we make our figure 2 times bigger? I'd say we did. Okay. Now, the only issue is that as we look at our graph, our center of dilation is at the origin, right? Okay. But I moved it down there. Do you think I could move it back? Sure, why not? Okay. So let's take all of these points and move them back up 4 and left 2 and see if that fixes where our center of dilation is. So if I go back up 4 and left 2, this point becomes right here. If I go up 4 and left 2, I believe that ends up right here. Okay. And then if I go up 4 and then left 2, I believe that ends up right there. Let me switch colors so this is easier to see. So at the end of the day, I ended up with a figure right there. All right, let's examine this for a second. This figure is 2 times bigger than this one, right? Okay, so that's good. And does it look like it's exploding outwards from -2, 4? Absolutely. Okay, it looks like this is the point from which it's just completely going outwards from. Sweet. So I think we just figured out how to do a center of dilation that's not at 0, 0. So to summarize, basically we moved it so that it was easy to multiply, and then we moved it back. Okay, so it's gonna, so doing dilations with a center not at 0, 0 is just gonna involve a little bit of translating, and then the dilations just like you're used to doing. Okay, we'll practice this several times. All right, don't worry. Okay. All right, so in your packet it says when the origin is not the center of dilation, you need to subtract the coordinates of the center of dilation from the coordinates of the preimage, multiply this difference by the scale factor, and then add the coordinates of the center of dilation. Take a couple seconds and digest that for a second. Do you agree with what they're saying there? Yeah, okay. Basically, that's what we did. I mean, we did all the moving around on the graph, but if you were doing the translations just with the coordinates, the translations would involve subtracting the coordinates of the center of dilation, moving it all to 0, 0, multiplying, so that was when we did the dilation, and then adding the coordinates back in was when we moved it back to where the center of dilation was originally. So yeah, that's a pretty accurate way of saying that. Okay. All right. So let's try this out then. Okay, so this is 18A, if you want to skip ahead in your packet there. So it's under the check your understanding. Okay, so we have a triangle with these coordinates, and we are wanting to do a dilation with a scale factor of 1/2 and a center at 2, -3. Okay, so let's try this out. So I'm going to recommend, kind of like when we did that composition of transformations yesterday, let's make a nice little chart here, because we're basically going to be doing several transformations here back to back. You need 4 little columns. Okay. All right, so let's start with our preimage. So we would either need to read those off a graph, or in our lucky case, they gave them to us. So we're starting out with the points 6, 4, -4, 2, and 2, -3. Okay. All right, our first task, since the center is not at 0, 0, is to move it so that the center would be at 0, 0. So envision a graph, if you have the point 2, -3, it's down here, right? So I would need to move it left 2 and up 3 to get it to 0, 0. So that would involve taking the x's and minusing 2, taking the y's and actually adding 3, right, to come up 3. Okay, So let's do that to all of our points here. So 6 minus 2 is 4. 4 plus 3 is 7. Negative 4 minus 2 is negative 6. And 2 plus 3 is 5. All right, 2 minus 2 is 0. Negative 3 plus 3 is 0. Perfect. All right, so there's our coordinates after we moved it, okay? Remember, after we move it to 0, 0, I need to dilate it. So to dilate, I just multiply by the scale factor, right? So I need to multiply by 1/2, okay? Which means basically taking half of all these, right? So half of 4 is 2. Half of 7 is 3.5. Half of negative 6 is negative 3. Half of 5 is 2.5. All right, and half of 0 is still 0. Half of 0 is still 0. Okay, awesome. So then now that my figure is half its size, I just want to move it back now to where the center of dilation was supposed to be. So remember, now we're at the center, so I just need to move it back over 2 and down 3. So going over 2 involves adding 2. Going down 3 involves subtracting 3. All right, here we go. So 2 plus 2 is going to be 4. 3.5 minus 3 is just going to be 0.5. Negative 3 plus 2 is going to be at negative 1. And then 2.5 minus 3, that would actually be negative 0.5, right? Okay. And then 0 plus 2 is 2. 0 minus 3 is going to be at negative 3. All right, so this is purportedly going to be my coordinates, right? Okay, I can graph it real quick if I wanted to kind of get an idea. So if I do a quick sketch of this graph, okay, the original figure was at 6, 4, negative 4, 2, and 2, negative 3. And by the way, you don't have to sketch this graph. This is just for illustration purposes. And then the figure that we ended up with is at 4.5, so just right here. Negative 1, negative 0.5, and then 2, negative 3, which is right here. Yeah, so it looks to me like that figure is half its size, and it looks like it explodes outwards from this point down here, which is good, because that's what we wanted the center of the dilation to be. Awesome. All right, skipping ahead here, okay, so going to question 21, okay? So just to kind of get an idea here of what dilations are doing in general, okay, because, you know, we won't do dilations with a different center all that often, you know, mostly we'll just be doing them with centers at 0, 0. But in all cases, dilations are performing or doing kind of the same thing to a figure, okay? And that thing that they're doing to a figure is basically changing its size. So I'm going to say change size. But notice it never changes its shape. Okay, so all the figures we've done, you know, if it was a certain kind of triangle before it started, it was that same kind of triangle after we started. It was just changing the size of it. Okay, so as you look back at all of our dilations, okay, so this term preserve angle measures means to keep them the same. You'll notice that, yes, all the angles are congruent. Okay, that's how it keeps the figure the same. Okay, so it's the same shape because all the angles are the same size. You know, think of like a square. If I dilate a square, it has 90-degree angles before it started and it has 90-degree angles after it started. Okay, now even though it keeps angles measures the same, it doesn't necessarily keep the side lengths the same. So would you consider dilation to be a rigid transformation? No. Okay, because the sides change length. Okay, so this leads us to a really great kind of thing to know about dilations. Okay, in dilations, the angles are congruent, and the sides are something that I'm going to call proportional. Proportional meaning that they all get bigger. But they all get bigger or smaller by the same amount. So, you know, if it's 2 times, if the dilation is by a scale factor of 2, all the sides are 2 times bigger, even though they can be different lengths. Okay, so this is a really important thing to keep in mind, because in the future we're going to really compare dilations to similarity, and that's how we're going to understand similarity. All right, So just a quick little check of your understanding here, and this is actually going to be in the next video. So click on the next link, please.